Okay, so this video is a bit more technical. We're going to prove a theorem about reparametrization of curves or paths in R3, but we write it in Rn in general. So to do that, what we mean by that is that if we have two paths that basically represent the same curve, think of cosine t, sine t from 0 to pi, or cosine 2 pi t, sine 2 pi t from 0 to 1. Those two are the same curves, only that one goes faster than the other. So these are going to be called reparametrizations, one of the other. So the technical thing here that I'm saying is if you have a gamma curve from A, B, an interval to Rn, the piecewise, the C1 part means it's continuous with first derivatives continuous. So it's a short way of saying that. So piecewise is that you can cut it into intervals, and that in each piece of that subinterval it's continuous and first derivative is continuous. So you have a curve like this. Then a different curve, beta, is going to be called a reparametrization. Oops. If there is a function u that takes the intervals of the domains of a, b to c, d, such that beta becomes a composite function of gamma with u. So what this is saying in a little diagram, it means something like this. So if I have my R3, if I have, for example, my interval AB that gets sent to my R3 in a certain way, say this is my gamma function, or the image of my gamma, then I'm going to have a different interval CD. It might be longer, it might be shorter. Also, I'm here to Rn. And then there is a function u that takes the AB to the CD. So this is my function u that goes here. And what that function, I want to have a little dot up here. What that function u does is that if you take, I'm going to use this dot to move it around. If you take this dot, a point in here, and you move it with u function here, I don't know where it lands, okay? But then you move it with the beta function, and it will land over here, okay? And the whole point, sorry, maybe I need to draw something else. Let me pretend this is my point t, and that point in the AB interval sends to this guy. So what this is saying is that if I grab it here, and I send it somewhere here, I don't know where it lands, and then it goes over here, it goes to the same point that if you would have came from the gamma function. Okay. So sending the point from here down to this interval, and then the beta, you get saying that if you take it directly from the gamma. That's what this is saying. That's what this condition is saying right here. Okay. Now, something to be aware of is that it doesn't have to take these points close to A to points close to C to do it over here. It could happen that this point gets sent somewhere over here, and that point goes over here, right? So basically, it could be that it reverses the orientation, and that's what we're going to be talking about. So we have one more thing to add to the definition. I didn't add it before to have a little bit of space. But let me now make this a little bit smaller so we have space to add to that. Just put it over here. And let me put this guy over here in a picture. Just put it, I don't care if it overlaps, maybe it doesn't matter if it overlaps, just put it right there. That looks good. Okay, so what I need to do is I'm going to talk about what I just said about reverses orientation. So one more bullet to add to my definition is that we will say that, like I said, the two options is that u of c is A and u of b is D, which follows the same order, or u of c, sorry, the u is backwards. I wrote it backwards, so I wrote it almost right in inverse. u of A is C and u of B is D, or u of A is D and u of C, I got it wrong, u of B is C. Correct. Those are my two options. It either sends the A to the C and the B to the D, or it sends the A to the D and the B to the C. So one of these, we're going to say reverses or preserves orientation. So we're going to say that beta preserves orientation, which means the orientation of given by gamma. Beta preserves orientation if the first condition was met. If u of A is C and u of B is D. And beta reverses orientation if it goes backwards. If u of A is D and u of B is C. Now, as a function between the AB and the CD intervals, look at what's happening. So let me just make a small picture here. As a function, the u is a function between two intervals. The AB, which I can put it here, and the CD, which is over here. So just like a function in Calc 1. So in the first option, and put here, in the first option, this is a one-to-one function, right? Sorry, I didn't say that. I should write here. If there is a one-to-one function, that should be important here in my definition. Okay, that's important. So it's one-to-one, which means it's and it takes the intervals to the interval. So which means it's onto, and it covers the whole interval, and it's one-to-one. It takes the whole interval. So that means that my only option in case A is that it goes, I don't know what's going to go in here, but it can do something like that, right? And in my second option, it goes backwards. The A goes to the D, the B goes to the C, and it is decreasing, right? So when I want to say, so this is in 1, this happens in 2. So here, the derivative is positive, right? It has to be an increasing function, and over here, the derivative is negative. It has to be a decreasing function. Always increasing, always decreasing, because I added that it's now one-to-one function. Right? That's why it's important. Okay. Okay. So with that, now we can prove the theorem we want, which is that if you have a reparametrization of a curve, then the line integrals are the same. And this is a scalar line integral. Okay? F is a scalar function. The ds is our differential of arc length. So we're not doing a vector line integral yet. We'll come to that in a later video. So to prove that this is true, there's nothing fancy to do. Just go ahead and start writing what this line integral is. So the proof just says, well, let's integrate. Let's start with the right side. The integral of beta of f ds. The definition of this line integral is you're integrating from the domain of your curve, which is c to d, and being beta. Okay, this is beta from here, but it is a reparametrization. So that means that, remember from the past, that just means that beta is gamma of u for a certain one-to-one function u that takes the AB into the CD. Okay. So the f is, the line integral f ds just becomes the line integral from c to d of f of beta times the magnitude of beta prime, that's the definition, and dt. Okay, this is the definition of a scalar line integral. Okay, now let's plug in who beta can be written as gamma of u. So it's beta of gamma of u. Here I'm going to write the magnitude of beta, sorry, not beta of gamma of u, this is f of gamma of u. It's a little bit weird. And here's going to be beta is gamma of u prime. So beta prime would be gamma prime at u times u prime. Just a chain rule, right? So it would be the magnitude of gamma prime at u times u prime. Okay. And then from there, I can write this like, or I can break this up like two absolute values, like the magnitude. These two things are, this is a magnitude, but the u prime is a scalar. So I can break it up like this. Okay. I'm using simple bars for magnitudes and absolute values, but it's the same notation. It's the distance from the origin. So in this case, it's a vector, but in this case, it's a scalar. But it's the same thing. And now I'm going to use a fact I have to split into cases, right? If u preserves orientation, so if beta preserves orientation, then u prime, this part, is positive, so I don't need the absolute value. So this is the same as c to d of f of gamma of u, magnitude of gamma prime of u. This is u prime of t dt. Because in this case, if it preserves orientation, u prime of t is positive. So this term right here, the inside is this absolute value is positive, so I can just erase it. Why am I doing that? Because now these two terms together, I had u prime of t dt. I can change it for a du, right? If I had in differential notation, this is u prime dt. So what I really have now is this. I want to change the variables. We have an integral of f of gamma of u, gamma prime of u, du. So I'm changing the variable. But and then my limits of integration change. So I need to find out u of c and u of d. But in this case, it's where I'm here, and sorry, I'm doing this backwards. So if u of c goes here, u of a is c. I'm doing it backwards, so I think I had it in the right direction backwards. So c would go to a if I see it backwards, and d would go to b. But it's the same. It's 1 to 1, so it doesn't matter. So the u goes to a, and the b goes to b. And this is exactly the definition of the line integral. Now you treat the u like your dummy variable, and it really just is from a to b of f ds, right? It's just f of gamma prime dt or du. So I started with the integral of f ds with beta, and now it's f ds with gamma. So now what's left over is the other case. What happens if beta reverses orientation? Well, in that case, this still looks the same. The difference is that this term here is negative. So in that case, the absolute value of u prime is the negative u prime, or the opposite, right? Because the u prime is negative. So this negative outside will make it positive. So this will include, I have to add a negative sign over here. I can take it outside of the integral that comes from this part, okay? But everything else looks the same. I have the gamma prime of u. I have u prime. That part is negative, but I have the negative outside to make it positive because that took the absolute value. And now I want to do the same thing. I'm going to change this for du. I want to change nothing here, f gamma of u, magnitude of gamma prime of u. Move my du up here. The difference is that now I have my negative outside, but now reverse orientation, so my C is not going to A, it's going to B, and my D is not going to B, it's going to A. So here I have like two things going on, where I have the integral negative outside, but my limits of integration are backwards. So I can change the limits of integration and put them A to B, and then that gets rid of this negative sign right here. Right? If you reverse the limits of integration, you get the negative of the integral, and then it's the same thing. F of gamma of u, gamma prime of u, du, which is the integral of the same as this one. Okay. So as expected, reparametrization of the same curve does not affect the scalar line integral.